Hi everyone. I'm Yoshi. I'm a PhD student here at Monash. In my second year now, I'm working with Amanda Karagas and Simon Campbell. Today I wanted to talk to you about the work I've been doing from the first year of my PhD, which is focused on S-type stars, so S-type AGB stars. And I'm looking to constrain their masses using their pulsation, which I'll explain in a bit. So just to situate myself in the whole realm of the conference, I'm looking at low to intermediate mass AGB stars, specifically on the thermally pulsing AGB, so characterized by strong mass loss, pulsations, interesting nucleosynthesis and chemistry. And I do want to talk about what I want to know about these stars. Um, I've seen a lot of interesting stuff this week. So now, just to revise a little bit about thermal pulses and the third dredge-up in AGB stars. So we get to a point in the star's life where we have this double structure of burning shells within the star. At some point, the interior helium burning shell can become thin enough so that there's a thermal instability and there's thermal runaway. So there's a flash, and that will drive out the outer layers of the AGB star and temporarily extinguish the hydrogen burning shell, allowing convection in the intershell region to bring out things from inside. This is the third dredge-up and changes the carbon on the surface. Also can bring up some S-process elements. And if the thermal pulses are strong enough, that's when the dredge-up happens. And if there are enough dredge-up events, you can become a carbon star. So there's a big uncertainty in current models of thermally pulsing AGB stars, and that is that the lowest initial mass where you can have the dredge-up is not well constrained. So if we look at observations and models of trying to constrain this quantity, we have the minimum initial mass to make a carbon star. Observations such as those of the carbon star luminosity functions in the Magellanic Clouds kind of suggest about 1.5 solar masses at solar metallicity. Models, you need to add some extra uncertain physics to kind of match this. What about the initial mass for the third dredge-up to occur? This is slightly different. So maybe it's lower than 1.5 solar masses, such that you don't actually get to a carbon-rich star. And again, in models, that's where it's uncertain. So how do we address this? So we look at S-type AGB stars. Now, of course, you can start with an M-type star, and if you have enough dredge-up events, you can get to S-type, which is carbon-oxygen between 0.5 and 1. These are thought to show the earliest signs of dredge-up. And of course, more dredge-up events, you may get to a carbon star. You do need to be careful though, because you can also make S-type stars extrinsically by accretion of carbon-rich material from a former star that was an AGB and is now a white dwarf. But a nice way you can kind of disentangle the intrinsic and extrinsic S-type stars is to look for technetium, which is a radioactive element produced by the S process that has a quite short half-life relative to the thermally pulsing AGB phase. So if there's technetium, there's likely ongoing S process. Also, AGB stars are variable stars. They're long period variables, as a lot of talks yesterday and today have explained. You can have semi-regular variables. These are general labels where you can see multiple variability periods. I said not necessarily pulsation because of long secondary periods. And you have your Myras, your wonderful large amplitude long period variables. And if you plot a period luminosity diagram such as this, you can see pulsation sequences that have been associated with the radial pulsation modes of these stars. So generally, as AGB stars evolve, they move to longer pulsation periods, go down to lower radial order modes and grow in their pulsation amplitudes. Now, there are some models of stellar pulsation in AGBs that are available and kind of interface nicely with detailed models of AGB stars. You might notice that the fundamental mode periods are quite crazy here in this plot. That is corrected in a later paper by Chibuchi in 2021 because you need to treat the fundamental pulsators a bit differently. Anyway, so that's one of the motivations for what I'm doing. So a lot of the time, the Magellanic Clouds have been very useful for AGB theory in general. Carbon star luminosity functions, as I mentioned, also looking at pulsations, they're all at the same distance, so you can find very clean period luminosity relations. I've been looking at the galactic AGBs. Another motivation is that there are some more recent studies that look at S-type star masses and try to estimate them. Chettier et al. In 2021 found that there were some S-type stars that seem to have initial masses down to around 1 solar mass, which is quite low to see signs of dredge-up. There is this paper from Marigo et al. In 2022. There were only 3 MS and S-type stars in the sample. They are quite rare in the scheme of things. They were around 2 solar masses. The masses are quite difficult to constrain, such as from like the Hertzsprung-Roxelver diagram here, just because of the long-term variability and variability due to the thermal pulse interpulse cycle. And another motivation is that there's a lot of new data. Gaia DI3 with parallaxes and hopefully better luminosities, hopefully, for galactic AGB stars, and large surveys of variability, such as those from ASAS-SN. Now, the goals of what I've been doing is to estimate the initial stellar masses of intrinsic S-type AGB stars by comparing their pulsation periods and luminosities to stellar models. And I want to use these masses to place further constraints on the lowest initial mass that the dredge-up can happen. A lot of these results are very preliminary. Currently writing a paper. So the general plan is to collect a sample. I want to analyze the light curves for these stars to find pulsation periods, derive luminosities, and then just compare these to stellar models to estimate some initial masses. Seems simple. So first, collecting the sample of intrinsic S-stars, there are many papers that classify S-stars to be intrinsic or extrinsic using either technetium or other methods. I am more trusting of the technetium compared to the other methods, but so I've included the methods as technetium maybe. There are some more papers that have all technetium yes stars. There are also some curious technetium-rich M and MS stars in the Untenthaler sample. I then make some cuts to the samples from these just because of Gaia not really having great parallaxes for a lot of AGB stars. And I also make some cuts for ASAS-SN light curve quality, as many of these stars are bright, so they do saturate some of the, well, they do saturate the ASAS-SN bands. And I end up with about 345 stars, about 98 with technetium measurements in the literature, and maybes about 247. This is a bit more of a breakdown of the Sinbad spectral types on the left. There are a couple carbon stars apparently in my sample of F-stars. In the literature, these apparently recently switched from SC to C in spectral type. The ASAS-SN catalog also provides some machine learned variable types. Most of the sample are classified in this way, but hopefully through my light curves, I can classify them again. So here's an example of some light curve analysis. I use the Lomskagel periodogram to deal with the scattered light curves. I take the peak periods that I find, periods that I find from the periodogram. I check them with a phase plot as well, just to see if they aren't effects of windowing from the baseline signal. There are a lot of different types of light curves in these semi-regular stars. Not really restricted. No real patterns between the technetium yes and technetium maybe samples. Some of them you do see almost pretty clear long secondary period-like behavior with shorter, smaller amplitude variability as well. So this is a period luminosity diagram combining the ASAS-SN catalog variable stars with two-mass photometry and Gaia or the Baylor-Jones distances with some parallax uncertainty cuts. You can see that we do resolve the period luminosity sequences, which is quite nice to see. I've also colored them by the ASAS-SN G-band amplitude just to see the sequence for the Myras here, or the fundamental mode pulsators. We can kind of see second overtone mode pulsators, first overtone, and the fundamental mode pulsators, also secondary periods. And I try to assign a mode to the periods that I've found from the periodogram. This can be quite uncertain, as mentioned many times, from the Gaia parallax uncertainties, but also some saturation in the two mass K magnitudes if I plot them like that. Distance uncertainties, also potential metallicity effects on the pulsation periods. So I measure a bunch of periods as such. I've also included the long secondary periods in this plot because that's also interesting. I've assigned this one, for example, as a likely first overtone mode period. For the light curves that have multiple variability periods, I use an iterative pre-whitening process, which is just removing the sinusoid of the highest periodogram peak from the light curve and then reanalyzing that light curve. This was kind of a nicer example of a light curve. A lot of them are saturated, as I have said. So the luminosities, I use the Baylor-Jones distances once again, and extinction maps from Bollerman et al. I check two different luminosity determination methods, just some simple bolometric correction relations for M-type stars that have been used in the literature for S-type stars, and some SAD fitting with VOSA. Just to compare the results from these two, you do see similar spreads of the luminosity, which is quite heartening. Just once again, as a one-to-one plot, there is just some scatter. There doesn't seem to be an actual offset towards each, which is also quite nice. But for the uncertainties, once you propagate them, you see that the when using the two-mass photometry, a lot of them are just saturated. So that does affect the bolometric correction luminosities for those uncertainties quite a bit. And I'm also, for now, hesitant to really trust the VOSA fitting uncertainties as well. So they're probably larger than I have here. Once again, uncertain parallaxes and distances, and yes, saturated. So I then compare the measurements I've got to detailed solar evolution models by Amanda. I have a grid between 0.9 to about 5. I might extend that slightly on the higher mass end just to capture these ones. These are the initial masses. I also have models of 3 different metallicities. And I've combined these with the non-adiabatic linear relation models, linear pulsation models from Chibuchi et al. In 2019. These take into account the opacity changes from the carbon to oxygen, but The carbon to oxygen actually only significantly affects the pulsation periods once you become carbon rich, so they aren't too affected for the S-type stars. Here's a result just from a simple, I suppose, grid interpolation between the models from the last slide. And I make a kernel density estimation just to take into account the uncertainties on all of the masses, just to smooth things out a bit. But I do have a histogram on the bottom. The peak appears to be between 1.3 to 1.4 initial mass, solar masses for the initial mass, at least, assuming a metallicity for these ones. Once again, this mass is lower than what the models of dredge-up really can reproduce. So maybe this is some evidence again that we do need to there's a lot to be done on the low mass end of the third dredge-up models. And there are also some intrinsic S-type stars that seem to have initial masses even below this peak value, which are even more difficult to explain with the current models we have. I have this slide also just to illustrate the effect of metallicity in the models and how that slightly shifts the peak initial mass depending on metallicity. I am still in the process of checking the effects of other uncertain model parameters, such as the mixing length parameter, as well as mass loss. So caveats on uncertainties. There are many. AGB luminosities have a lot of sources of uncertainty. The iterative pre-whitening method usually does work okay. It does sometimes suffer from really bad fits to the long secondary periods just because they might be longer than the baseline. So I could look into more flexible options like a Gaussian process regression. And also the mode assignment can sometimes be uncertain because of the above 2 points. And once again, there are more solar modeling uncertainties due to convection and opacities. And there's also the very strong assumption that there's a uniform metallicity for all these stars. We don't have really precise metallicities for these stars, unfortunately. And I would love to have metallicities so I could make better comparisons, at least compare apples to model apples instead of model oranges. But that's where we're at. So some things that I'm interested in next is some more modeling work to constrain the third dredge-up in these from, I guess, the modeling perspective. Maybe it might be worth increasing the number of known technetium-rich S-stars. There's, in the literature, a lot of focus has been on the Myras because they are very interesting stars. But the low luminosity semi-regular variables for this particular case are very interesting. And again, maybe some interesting seismic constraints can be learned from slightly other fields like astroseismology for thermally pulsing AGB stars. And there are also the curious technetium-rich M-type stars that seem to exist, and maybe these are the first signs of dredge-up in these stars. So, I'll leave my summary slide up there. Thanks for listening.
Hi, great talk. I'm curious, do you feel that you are more limited at this point by the models or by your observations? Like observations, I mean like specifically on like your measurement of the period and your measurement of the luminosity.
Yeah. I guess the answer would be the models, but the more, I guess, subtle point would be the connection between the observations and the models. I think there are the period luminosity sequences have evidence for which radial order modes they associate to. There is still some debate, I suppose, which of course, makes a lot of the conclusions quite uncertain. And that's why, yeah, the mode on the assignment is quite uncertain. So I was hoping to look more into fields like astroseismology to see if I can learn anything.
We should chat.
I'd love to chat. Yeah, yeah. Thanks.
Yoshi, you say that, so your second point there is that the
Yep.
lowest initial mass of the S-type AGB cells are lower than what you would think from the models. But what is the uncertainties on these derived initial masses? You know, the few attempts I have been doing, but then for oxygen-rich ones, they just, you know, they are so uncertain.
Yeah.
So what are these?
I'm still devising a way to really quantify the uncertainty on that.
Observed values.
Yeah, because it's a distribution of masses, right? So I'm still thinking of a way to quantify that uncertainty, but I don't know if that answers your question at all.
Not yet, eh?
Yeah,
Okay,
yeah.
let's work then. Okay,
It's a good question.
Yeah.
Yeah. So I don't know what
it's a bit as with the Hubble tension, eh? We need to know accuracy and precision, and then we can.
Yes. Yeah, I don't know what the lower bound to that is, but yeah, it's certainly interesting. But yeah, if you want to talk more about that, I'd love to.
Okay.
Yeah.
This is just a small comment regarding this second point. I think that you should not be very much worried about that differences, because that's also the models also are very, I mean, the error in the models are also very, the uncertainties in the models more than the errors, because this is extremely sensitive to convective boundary mixing treatment.
Yes.
And this is something that nobody knows. I mean, you have to calibrate it somehow. So maybe this is a way to calibrate that. So
I suppose that is more the aim. It's more the calibration to the models, because of course, you do need to listen to what nature is saying, right? And then that will inform your models. But yeah, thanks. Yeah.